I'm looking at subduction zones, and I'm Elliot, as it says there, so that's a good start. So I'm particularly looking at halogens and noble gases, but also, in a wider sense, volatiles. Oh, lovely. That's great. So once that's disappeared, I'll bring up a big cartoon of a subduction zone to check we're all on the same page. So this is what we understand to be the structure of the Earth. So oceanic crust is formed at a mid-ocean ridge where the mantle melts, and this sort of travels very slowly over hundreds of millions of years along the ocean floor, where it's altered by seawater. So that brings in volatiles from the atmosphere and from seawater that are incorporated into that plate. And eventually, say at the edge of the Pacific on the Ring of Fire, that starts to go down into the deep mantle. And here, as it starts to heat up and experiences higher pressure, a lot of that water and other volatiles are expelled into the mantle above, causing melting, and much of those volatiles are returned to the surface in volcanic arcs. So these will be the volcanoes that Ben was studying in Guatemala. So the central question I'm really looking at is, does the influx coming in down here equal the outflux here, or is the net transport to the deep Earth? And so as an example here, I've got just a set of estimates for chlorine, just everything I could find in the literature. Essentially what this shows, it's a box plot, but basically if you take one estimate here and one here, you can have the balance one way, or you can have it totally the other way. So essentially we do not know this. So does that matter? So yeah, why does this matter? The volatile set, apart from being like a really huge, this is a central coupling of the deep Earth and the surface of the Earth. So apart from that just being interesting, it also helps us understand a lot of other questions. So one is the timing of atmosphere formation. So we use what's called the iodine xenon clock to date exactly when our atmosphere closed, when we stopped losing gas to space, and that's sensitive to how much xenon or iodine we're subducting down these things. It helps us understand what's going on in the deep Earth in terms of structure and dynamics. And a last one, which I think is quite interesting, is it might have implications for the habitability of Earth. So it's been suggested that if we're subducting huge amounts of chlorine, or significant amounts of chlorine, that might buffer the surface salinity of Earth. So one of the key differences, say, between Earth and Mars is that Mars does not have subduction zones. It doesn't have plate tectonics. So perhaps we would expect, without plate tectonics, most of the chlorine to be concentrated at the surface, and maybe that's a key difference between Earth and Mars if significant amounts of chlorine and other volatiles are subducted. So, existing attempts to sort of look at this mostly rely on either looking at the output we get from volcanoes to quantify the outputs, or looking at oceanic drill cores, so drilling into the ocean crust to look at the inputs. And the key problem with drilling into the ocean crust, which is that we've never got beyond about 2 kilometers thickness, whereas we think the ocean crust is at least around 7 kilometers thick typically, and beyond that there may well be water incorporated into greater depths of the lithospheric mantle. So what I'm planning to do, or what I am doing, is looking at ophiolites. So ophiolites are sections of crust and mantle which have been put up onto the continents by tectonic processes, and these give us a place where we can look at much deeper layers, and they also give us a place where we can look at subduction zone outputs as well, because typically the way they are placed onto the continents is by some kind of buckling of a subduction zone, which leads to an area of mantle being shunted up on top of the continents where we can go and look at it. So the one I'm looking at is called the Liker ophiolite complex, which is in Norway. And this is what a section of that, the mantle section, looks like. And essentially the simple model that we're sort of taking as a starting point is that what we have here is a load of mantle that was altered by seawater. This is what we're hoping. All this blue stuff was altered by seawater. That represents the input to a subduction zone. As that is then ridden over a different subduction zone as it's been placed onto the continent, melts leaving that subduction zone have crossed this mantle and left these dikes. It's shown in red here. So these are stuff that has seen a lot of the material leaving the slab. So the idea here is that we have both inputs and outputs represented in the same place with a common geological history. So that's just a little sort of reiteration of that. So what we're going to look at is noble gases and halogens. So we measure these both as noble gases, and I'll come on to the halogens later, but the way we extract gas from these is either by crushing or by heating. And this lets us look at different aspects of the same minerals. So by crushing, you can see here this is a microscope image that's maybe a field view of 0.5 millimeter or less. we have these tiny fluid inclusions, little pockets of liquid or gas, trapped within the crystal as it's formed. So when we crush, we release these, but any gas actually dissolved in the matrix of the mineral will be left behind. If, however, we heat it, then we release everything. We melt the mineral and we release all the gas. So we can look at complementary processes and different signatures within the same samples. So I'm going to move on to some results. So these are, first off, these are crushing data from noble gas crushing data. And in blue, just like the map we saw, we've got Habitability. So these are what we think are the inputs to the subduction zone. And in red, we have the dikes, the subduction-related dikes that we think are representing the outputs. And hopefully you can see here, these are quite different. So these two black points down here are air at this corner and seawater here, which I should have labeled. And we see that we've got, so on this axis we've got argon isotopes. So argon 40 is produced by decay of potassium. Argon 36 is what we call non-radiogenic. And here we've got the relative abundance of krypton and argon. And krypton is elevated in things like sediments and in the oceanic crust. And what we see is that in our subduction-related samples, we have both elevated amounts of argon and elevated amounts of argon 40 and elevated amounts of krypton. And in our mantle Habitabilities, the things we think just represent the stuff that's sitting at the bottom there, these plot very nicely just between seawater and air, which is exactly what we'd expect if they've only been altered by seawater. So these are data where we've just crushed the thing once. We've crushed almost all the gas we can get out of it at once. We can also step crush, which is do lots of little steps and see how it changes. So these are the data we get from that. So we've done several of these higher argon and more enriched things. And we get this interesting progression down to the right. As we crush, each of these represents one analysis. These are the data from the previous slide. We're slowly moving towards lower argon 40, but higher krypton. And I don't actually have a solid explanation for this, but it is intriguing that we're preserving some kind of heterogeneity within these single samples. If I just return here, it's notable, these grey points in the background are literature data from altered oceanic crust, and we see these form two big sort of limbs, one up that way and one up this way. And so my kind of tentative suggestion to explain these data is that we're actually keeping those relatively separate while we're forming these while we're forming the minerals that host this gas, and that somehow they're preserving both those limbs and are sort of mixing between those two. Quite how that works physically in reality, I'll have to work out. Maybe it doesn't. The other thing we find, so I've shown you we've got 40 argon elevated in many of our samples. So these are data now from heating our samples. You don't particularly need to worry about exactly the details of this. The main point is the bottom here. So these are our actual samples, and this is just a smooth curve I put on because it looks nice. But we've got some with ages of 5 billion years, so hopefully most people know the Earth is not 5 billion years old, so that cannot be a real age. So we have here a lot of argon 40 that cannot be explained by potassium in the rocks. So this is what's called argon-argon dating. We have excess argon, so it's a meaningless age. What it means is that argon 40 has to have come from somewhere else. And a very likely source of that is oceanic crust, which has high potassium. So the argon 40 grew in a high potassium place in the crust, and then has been incorporated into our samples. So lastly, we also see a difference. So when we've heated these, so this is the same plot. Well, we've got xenon, but xenon and krypton are very similar in their behavior. So this is the same plot, but now we have heating data as well. So this is the data I showed you on the previous few graphs. And the heating data are markedly different. Once again, don't really have an explanation for this. There's a theme in this talk, which is the more and more data I've collected, the less clear everything has become. So if anyone's ever seen me before, I've been really confident. I've been like, yeah, we know exactly. I have no idea what's going on. But there is definitely some difference. And essentially what we see here is seawater and air about here. So everything heated is plotting between seawater and air in terms of its xenon abundance. But we're still seeing this elevated argon. So I guess the main takeaway is there is definitely some value in crushing these samples, and that will become relevant later. We're seeing something else, something that's just been trapped as a fluid, rather than something that's incorporated within the mineral. We're seeing different signatures. So as I said, I'm also going to talk about halogens. So we measure halogens in kind of an interesting way, and that is by putting our samples in a nuclear reactor. So I briefly mentioned argon-argon dating. This is a sort of extension of that, method. So this is a series of nuclear reactions for bromine. So we bombard that with neutrons, and we actually turn those into, or a proportion of the bromine present in our rock, we turn into noble gases, which we then detect on a noble gas mass spectrometer, just as I have the unirradiated samples. And the particular advantage of this is you can get incredible detection limits. So I can measure down to a part per billion in about 5 milligrams of rock. So it's very useful. It's often used for like meteorite samples that are incredibly precious, but for mine it also is very useful. So this is the data I've collected so far, and once again, I do not know what it means, but it is interesting. So in the background, this scatter of plots in grey and in red are literature data. The black are serpentinites, so these are what we think has been altered at the base of the seafloor, below the ocean crust. In red are data for altered oceanic crust, and in a rainbow of colours, slightly bigger, are my points down here. So the thing that really surprised me is they look nothing like the serpentinites. At first I thought, okay, this is actually a problem, we've done something wrong, but the more I've checked it, we haven't. We do have very low bromine compared to chlorine. So these, on this axis we have bromine relative to chlorine, this one iodine relative to chlorine. They're plotting very low, but something they are plotting near is a certain element of altered oceanic crust. So a possible explanation for this is looking at, so this is again literature data from those red points. If we look at the depth of these, something that does sort of match our samples is these shallow parts of the oceanic crust where we sometimes have high iodine to chlorine and also find low bromine to chlorine ratios. Whereas as we go deeper in the crust, we generally see low iodine to chlorine and higher bromine to chlorine. So potentially what we're seeing here is very shallow expulsion of volatiles from the altered oceanic crust that's subducting beneath our ophiolite slice. So this is a bit closer up on this area, just to sort of see that most of our samples lie in a bit of a cluster here. All these green ones are olivines, and olivine, when it's altered by water, turns to a mineral called serpentine. I've also got a bit of a suggestion maybe of some kind of mixing to another component over here. Again, I don't know what that is. So just lastly, we've also done some in situ work on the electron microprobe to look at where our halogen site is. So the only one we can reliably measure on the probe is chlorine, so that's the map of it here. We've got magnesium and iron that just give you an idea of some of the minerals. So this is olivine, this is the chromite, and the red here is all our chlorine. We've got some really quite high concentrations, and this is all cited in the serpentine. And the point of this is that, to go back to this one, our cluster of green points here is entirely dominated by the serpentine that's clung to those olivines. It's very hard to separate the two. So as our sort of next step, what we will be doing is trying to step heat, so very gradually heat our samples in the hope that the stuff here will break down at a lower temperature than this stuff, and we might be able to resolve the separate signatures in both and get more of an idea of what's actually going on here. So, have we learned anything? I'm not sure. Maybe. Sort of returning to the original question, if we look at the noble gases, there's clearly a difference between our mantle, what we're saying might be an input samples, and our dikes related to this subduction melting and melt percolation. However, it's kind of confusing that this difference it's not expressed in any way in the halogens, and that's a bit of a puzzle to me. So another thing I want to do, as I said earlier, crushing gives us complementary information. I want to crush these samples that have been irradiated to see what kind of signatures are released from the fluid inclusions. We also seem, in every case, to have some kind of altered oceanic crust signature, but actually getting that to the next stage of saying that 100% came out of the subduction zone is more difficult. So, I don't know, it's up in the air. You decide. So I'll just leave that up. Thank you very much.